Andesite commonly exhibits a porphyritic texture. When this is the case, the phenocrysts are often light, rectangular crystals of plagioclase feldspar or black, elongated amphibole crystals. Andesite may also resemble rhyolite, so its identification usually requires microscopic examination to verify mineral makeup. Diorite. Diorite is the intrusive equivalent of andesite. It is a coarse-grained rock that looks somewhat like gray granite but can be distinguished from granite because it contains little or no visible quartz crystals and has a higher percentage of dark silicate minerals. The mineral makeup of diorite is primarily plagioclase feldspar and amphibole. Because the light-colored feldspar grains and dark amphibole crystals appear to be roughly equal in abundance, diorite has a salt and pepper appearance. Mafic igneous rocks. Basalt. Basalt is a very dark green to black, fine-grained rock composed primarily of pyroxene and calcium-rich plagioclase feldspar, with lesser amounts of olivine and amphibole. When it is porphyritic, basalt commonly contains small light-colored feldspar phenocrysts or green, glassy-appearing olivine grains embedded in a dark ground mass. Basalt is the most common extrusive igneous rock. Many volcanic islands, such as the Hawaiian Islands and Iceland, are composed mainly of basalt. Further, the upper layers of the oceanic crust consist of basalt. In the United States, large portions of Central Oregon and Washington were the sites of extensive basaltic outpourings. At some locations, these once fluid basaltic flows have accumulated to combined thicknesses approaching 3 kilometers. Gabbro. Figure 4.15 basaltic lava flowing from Kilauea Volcano, Hawaii. Gabbro is the intrusive equivalent of basalt. Like basalt, it tends to be dark green to black in color and composed primarily of pyroxene and calcium-rich plagioclase feldspar. Although gabbro is uncommon in the continental crust, it makes up a significant percentage of oceanic crust. Pyroclastic rocks. Pyroclastic rocks are composed of fragments ejected during a volcanic eruption. One of the most common pyroclastic rocks, called tuff, is composed mainly of tiny, ash-sized fragments that were later cemented together. In situations where the ash particles remained hot enough to fuse, the rock is called welded tuff. Although welded tuff consists mostly of tiny glass shards, it may contain walnut-sized pieces of pumice and other rock fragments. Welded tuff deposits cover vast portions of previously volcanically active areas of the western United States. Some of these tuff deposits are hundreds of feet thick and extend for more than 100 kilometers from their source. Most formed millions of years ago as volcanic ash spewed from large volcanic structures, sometimes spreading laterally at speeds approaching 100 kilometers per hour. Early investigators of these deposits incorrectly classified them as rhyolite lava flows. Today, we know that silica-rich lava is too viscous to flow more than a few miles from a vent. Outcrop of welded tuff that erupted from Valles Caldera near Los Alamos, New Mexico. Tuff is composed mainly of ash-sized particles and may contain larger fragments of pumice or other volcanic rocks. Pyroclastic rocks composed mainly of particles larger than ash are called volcanic breccia. The particles in volcanic breccia may consist of streamlined lava blobs that solidified in air, blocks broken from the walls of the vent, volcanic ash, and glass fragments. Figure 4.16 Welded tuff, a pyroclastic igneous rock. Unlike most igneous rock names, such as granite and basalt, the terms tuff and volcanic breccia do not imply mineral composition. Instead, they are frequently identified with a modifier. For example, rhyolite tuff indicates a rock composed of ash-sized particles having a felsic composition. Concept checks 4.4. 1. List the 2 criteria by which igneous rocks are classified. 2. How are granite and rhyolite different? In what way are they similar? 3. Classify each of the following rocks by their mineral composition. Gabbro, obsidian, granite, and andesite. 4. Describe each of the following in terms of composition and texture: diorite, rhyolite, and basalt porphyry. 5. In what way do tuff and volcanic breccia differ from other igneous rocks such as granite and basalt? 4.5 Origin of magma. Summarize the major processes that generate magma from solid rock. Based on evidence from the study of earthquake waves, we know that Earth's crust and mantle are composed primarily of solid, not molten, rock. Although the outer core is fluid, this iron-rich material is very dense and remains deep within Earth. So where does magma come from? Most magma originates in Earth's uppermost mantle. The greatest quantities are produced at divergent plate boundaries, in association with seafloor spreading, with lesser amounts forming at subduction zones, where oceanic lithosphere descends into the mantle. Magma also can be generated when crustal rocks are heated sufficiently to melt. Did you know? Since the 1930s, carpenters, mechanics, and other people working with their hands have used lava soap, which contains powdered pumice. Because of the abrasiveness of pumice, lava soap is particularly good at removing grease, dirt, paints, and adhesives. Generating magma from solid rock. Workers in underground mines know that temperatures increase as they descend deeper below Earth's surface. Although the rate of temperature change varies considerably from place to place, it averages about 25 degrees Celsius per kilometer in the upper crust. This increase in temperature with depth is known as the geothermal gradient. As shown in Figure 4.17, when a typical geothermal gradient is compared to the melting point curve for the mantle rock peridotite, the temperature at which peridotite melts is higher than the geothermal gradient. Thus, under normal conditions, the mantle is solid. However, tectonic processes trigger melting through various means, including reducing the mantle rock's melting point. This diagram shows the geothermal gradient for the crust and upper mantle. Figure 4.17 Full alternative text description. Decrease in pressure, decompression melting. Figure 4.17 Why the mantle is mainly solid. If temperature were the only factor that determined whether rock melts, our planet would be a molten ball covered with a thin, solid outer shell. This is not the case because pressure, which also increases with depth, influences the melting temperatures of rocks. Melting, which is accompanied by an increase in volume, occurs at progressively higher temperatures with increased depth. This is the result of the steady increase in confining pressure exerted by the weight of overlying rocks. Conversely, reducing confining pressure lowers a rock's melting temperature. When confining pressure drops sufficiently, decompression melting is triggered. Decompression melting occurs wherever hot, solid mantle rock ascends, thereby moving into regions of lower pressure. Recall from Chapter 2 that tensional forces along spreading centers promote upwelling where plates diverge. This process is responsible for generating magma along oceanic ridges where plates are rifting apart. Below the ridge crest, hot mantle rock rises and melts, generating a magma that replaces the material that shifted horizontally away from the ridge axis. As hot mantle rock ascends, it experiences continuously decreasing pressure. This drop in confining pressure usually initiates decompression melting in the upper mantle. Figure 4.18 Decompression melting. Figure 4.18 Full alternative text description. Decompression melting also occurs when ascending mantle plumes reach the uppermost mantle. If this rising magma reaches the surface, it triggers an episode of hotspot volcanism. Addition of water. Along with pressure, an important factor affecting the melting temperature of rock is its water content. Water and other volatiles, such as carbon dioxide, act in a similar way to salt melting ice. That is, water causes rock to melt at lower temperatures, just as putting rock salt on an icy sidewalk induces melting. The introduction of water to generate magma occurs mainly at convergent plate boundaries, where cool slabs of oceanic lithosphere descend into the mantle. As an oceanic plate sinks, heat and pressure drive water from the subducting oceanic crust and overlying sediments. These fluids migrate into the wedge of hot mantle that lies directly above. At a depth of about 100 kilometers, the wedge of mantle rock is sufficiently hot that the addition of water leads to some melting. Partial melting of the mantle rock peridotite generates hot basaltic magma whose temperatures may exceed 1,250 degrees Celsius. As an oceanic plate descends into the mantle, water and other volatiles are driven from the subducting crustal rocks into the mantle above. Figure 4.19 Water lowers the melting temperature of hot mantle rock to trigger partial melting. Figure 4.19 Full alternative text description. Temperature increase, melting crustal rocks. Mantle-derived basaltic magma tends to be less dense than the surrounding rocks, which causes the magma to buoyantly rise toward the surface. In oceanic settings, these basaltic magmas often erupt on the ocean floor, generating seamounts, which may grow to form volcanic islands, as exemplified by the Hawaiian Islands. However, in continental settings, basaltic magma often ponds beneath low-density crustal rocks. Because the overlying crustal rocks have lower melting temperatures than basaltic magmas, the hot basaltic magma may heat them sufficiently to generate a secondary melt of silica-rich felsic magma. If these low-density, felsic magmas reach the surface, they tend to produce explosive eruptions. Such eruptions occur most often at convergent plate boundaries. Crustal rocks can also melt during continental collisions that result in the formation of a large mountain belt. During these events, the crust is greatly thickened, and some crustal rocks are carried to depths where the temperatures are high enough to cause partial melting. The felsic magmas produced in this manner usually solidify before reaching the surface, so volcanism is not typically associated with these collision-type mountain belts. In summary, magma can be generated by decompression melting, caused by a decrease in pressure as magma rises, the introduction of water, which lowers the melting temperature of hot mantle rock, and heating of crustal rocks above their melting temperature. Concept checks 4.5. 1. What is the geothermal gradient? Describe how the geothermal gradient compares with the melting temperatures of the mantle rock peridotite at various depths. 2. Explain the process of decompression melting. 3. What roles do water and other volatiles play in the formation of magma? 4. Name 2 plate tectonic settings in which you would expect magma to be generated. 4.6 How magmas evolve. Describe how magmatic differentiation can generate a magma body that has a mineralogy that is different from its parent magma. Geologists have observed that a single volcano may extrude lavas that change in composition over time. Such observations led to the idea that magma might change over time and thus that one magma body could give rise to igneous rocks with a range of compositions. To explore this idea, N.L. Bowen carried out a pioneering investigation early in the 20th century into the crystallization of magma. Bowen's reaction series and the composition of igneous rocks. Recall that ice freezes at a specific temperature, whereas basaltic magma crystallizes over a range of at least 200 degrees Celsius of cooling. In a laboratory setting, Bowen and his co-workers demonstrated that as a basaltic magma cools, minerals tend to crystallize in a systematic fashion based on their melting temperatures. As shown in Figure 4.20, the first mineral to crystallize is the ferromagnesian mineral olivine. Further cooling generates calcium-rich plagioclase feldspar as well as pyroxene, and so forth down the diagram. This diagram shows the sequence in which minerals crystallize from a basaltic magma. Compare this figure to the mineral composition of the rock groups in Figure 4.12. Note that each rock group consists of minerals that crystallize in the same temperature range. Figure 4.20 Bowen's reaction series. Figure 4.20 Full alternative text description. During this crystallization process, the composition of the remaining liquid portion of the magma also continually changes. For example, at the stage when about 1/3 of the magma has solidified, the remaining molten material is nearly depleted of iron, magnesium, and calcium because these elements are major constituents of the minerals that form earliest in the process. The removal of these elements causes the melt to become enriched in sodium and potassium. Further, because the original basaltic magma contained about 50% silica, the crystallization of the earliest formed mineral, olivine, which is only about 40% silica, leaves the remaining melt richer in SiO2. Thus, the magma becomes progressively richer in silica as it evolves. Bowen also demonstrated that when the crystals that form in a magma remain in contact with the remaining melt, then they continue to exchange ions with the melt. As a result, the periphery of these mineral grains has a different, more evolved composition than the interiors. That is the significance of the arrows in Figure 4.20. Stated another way, minerals that remain in contact with a melt gradually change composition to become the next mineral in the series Bowen identified. This order of mineral formation became known as Bowen's reaction series. However, in nature, the earliest formed minerals can separate from the melt, thus halting further chemical reactions. The diagram of Bowen's reaction series in Figure 4.20 depicts the sequence in which minerals crystallize from a magma of basaltic composition under laboratory conditions. Evidence that this highly idealized crystallization model approximates what can happen in nature comes from analysis of igneous rocks. In particular, scientists know that minerals that form in the same general temperature regime depicted in Bowen's reaction series are found together in the same igneous rocks. For example, notice in Figure 4.20 that the minerals quartz, potassium feldspar, and muscovite, which are located in the same region of Bowen's diagram, are typically found together as major constituents of the intrusive igneous rock granite. Did you know? The formation of the most common chemical elements on Earth, such as oxygen, silicon, and iron, occurred billions of years ago inside distant massive stars. Through various processes of nuclear fusion, these stars converted the lightest elements, mostly hydrogen, into these heavier elements. In fact, most such elements found in the solar system, as well as in your body, are believed to have formed from debris scattered by stars that formed prior to the formation of the solar system. Magmatic differentiation and crystal settling. Bowen demonstrated that minerals crystallize from magma in a systematic fashion. But how do Bowen's findings account for the great diversity of igneous rocks? It has been shown that, at one or more stages during the crystallization of magma, a separation of various components can occur. One mechanism that causes this to happen is called crystal settling. This process occurs when the earlier formed minerals are denser than the melt and sink toward the bottom of the magma chamber, as shown in Figure 4.21. When the remaining melt solidifies either in place or at another location, if it migrates into fractures in the surrounding rocks, it will form a rock with a mineral composition that is more felsic than the parent magma. The formation of a magma body having a mineralogy or chemical composition that is different than the parent magma is called magmatic differentiation. A magma evolves as the earliest formed minerals crystallize and settle to the bottom of the magma chamber, leaving the remaining melt richer in sodium, potassium, and silica. Figure 4.21 Crystal settling results in a change in the composition of the remaining magma. Figure 4.21 Full alternative text description. A classic example of magmatic differentiation is found in the Palisades Sill, which is a 300-meter-thick slab of dark igneous rock exposed along the west bank of the lower Hudson River across from New York City. Because of its great thickness and consequent slow rate of solidification, crystals of olivine sank and make up about 25% of the lower portion of the Palisades Sill. By contrast, near the top of this igneous body, where the last melt crystallized, olivine represents only 1% of the rock mass. Recent studies indicate that the Palisades sill was produced by multiple injections of magma and does not represent a simple case of crystal settling. However, it is nonetheless an instructional example of that process. Assimilation and magma mixing. Bowen successfully demonstrated that through magmatic differentiation, a single parent magma can generate several mineralogically different igneous rocks. However, more recent work indicates that magmatic differentiation involving crystal settling cannot, by itself, account for the entire compositional spectrum of igneous rocks. Once a magma body forms, the incorporation of foreign material can also change its composition. For example, in near-surface environments where rocks are brittle, the magma pushing upward can cause the overlying rock to fracture into numerous pieces. The force of the injected magma is often sufficient to dislodge and incorporate blocks of the surrounding host rock. Melting of these blocks, a process called assimilation, changes the overall chemical composition of the magma body. Figure 4.22 Assimilation of the host rock by a magma body. Figure 4.22 Full alternative text description. Another means by which the composition of magma can be altered is called magma mixing. Magma mixing may occur during the ascent of two chemically distinct magma bodies as the more buoyant mass overtakes the more slowly rising body. Once they are joined, convective flow stirs the two magmas, generating a single mass that has an intermediate composition. This is one of the ways the composition of a magma body can change. Figure 4.23 Magma mixing. Figure 4.23 Full alternative text description. Concept checks 4.6. 1. Define Bowen's reaction series. 2. How does the crystallization and settling of the earliest formed minerals affect the composition of the remaining magma? 3. Compare the processes of assimilation and magma mixing. 4.7 Partial melting and magma. Composition. Describe how partial melting of the mantle rock peridotite can generate a basaltic magma. Recall that igneous rocks are composed of a mixture of minerals and, therefore, tend to melt over a temperature range of at least 200 degrees Celsius. As rock begins to melt, the minerals with the lowest melting temperatures are the first to melt. If melting continues, minerals with higher melting points begin to melt, and the composition of the melt steadily approaches the overall composition of the rock from which it was derived. Most often, however, melting is not complete, a process known as partial melting. Recall from Bowen's reaction series that rocks with a granitic composition are composed of minerals with the lowest melting temperatures, namely, quartz and potassium feldspar. Also note that as we move up Bowen's reaction series, the minerals have progressively higher melting temperatures, and that olivine, which is found at the top, has the highest melting point. When a rock undergoes partial melting, it forms a melt that is enriched in ions from minerals with the lowest melting temperatures, while the unmelted portion is composed of minerals with higher melting temperatures. Separation of these two fractions yields a melt with a chemical composition that is richer in silica and nearer the felsic end of the spectrum than the rock from which it formed. In general, partial melting of ultramafic rocks tends to yield mafic magmas, partial melting of mafic rocks generally yields intermediate magmas, and partial melting of intermediate rocks can generate felsic magmas. Partial melting generates a magma that is nearer the felsic end of the compositional spectrum than the parent rock from which it was derived. Smart Figure 4.24 Partial melting. Smart Figure 4.24 Full alternative text description. Formation of basaltic magma. Watch tutorial, Partial melting. Most magma that erupts at Earth's surface is basaltic in composition and has a temperature range of 1000 degrees to 1250 degrees Celsius. Experiments show that under the high-pressure conditions calculated for the upper mantle, partial melting of the ultramafic rock peridotite can generate a magma of basaltic composition. Further evidence that many basaltic magmas have a mantle source are the inclusions of peridotite, a rock that basaltic magmas often carry up to Earth's surface from the mantle. Basaltic magmas that originate from partial melting of mantle rocks are called primary or primitive magmas because they have not yet evolved. Recall that partial melting that produces mantle-derived magmas may be triggered by a reduction in confining pressure during the process of decompression melting. This can occur, for example, where hot mantle rock ascends as part of slow-moving convective flow at mid-ocean ridges. Basaltic magmas are also generated at subduction zones, where water driven from the descending slab of oceanic crust promotes partial melting of the mantle rocks that lie above. Formation of andesitic and granitic magmas. If partial melting of mantle rocks generates most basaltic magmas, what is the source of the magma that crystallizes to form andesitic and granitic rocks? Recall that silica-rich magmas erupt mainly along the continental margins. This is strong evidence that continental crust, which is thicker and has a lower density than oceanic crust, must play a role in generating these more highly evolved magmas. One way andesitic magma can form is when a rising mantle-derived basaltic magma undergoes magmatic differentiation as it slowly makes its way through the continental crust. Recall from our discussion of Bowen's reaction series that as basaltic magma solidifies, the silica pour. Ferromagnesian minerals crystallize first. If these iron-rich components are separated from the liquid by crystal settling, the remaining melt has an andesitic composition. Andesitic magmas can also form when rising basaltic magmas assimilate crustal rocks that tend to be rich in silica. Partial melting of basaltic rocks is yet another way in which at least some andesitic magmas are thought to be produced. Although granitic magmas can be formed through magmatic differentiation of andesitic magmas, most granitic magmas probably form when hot basaltic magma ponds below continental crust. When the heat from the hot basaltic magma partially melts the overlying crustal rocks, which are silica-rich and have a much lower melting temperature, the result can be the production of large quantities of granitic magmas. This process is thought to have been responsible for the volcanic activity in and around Yellowstone National Park in the distant past. Granitic magmas are generated by the partial melting of continental crust. Smart Figure 4.25 Full alternative text description. Smart Figure 4.25 Formation of granitic magma. Watch animation, magma rising from the mantle. Concept checks 4.7. 1. Briefly describe why partial melting results in a magma whose composition is different from that of the rock from which it was derived. 2. How are most basaltic magmas thought to have formed? 3. What is the process that is thought to generate most granitic magmas? 4.8 Intrusive igneous activity. Compare and contrast these intrusive igneous structures, dikes, sills, batholiths, stocks, and laccoliths. Although volcanic eruptions are occasionally violent and spectacular events, most magma crystallizes at depth, without fanfare. Therefore, understanding the igneous processes that occur deep underground is as important to geologists as studying volcanic events, which are the focus of Chapter 5. Nature of intrusive bodies. When magma rises through the crust, it forcefully displaces pre-existing crustal rocks, termed host rock or country rock. The structures that result from the emplacement of magma into pre-existing rocks are called intrusions or plutons. Because all intrusions form far below Earth's surface, they are studied primarily after uplifting and erosion have exposed them. The challenge lies in reconstructing the events that generated these structures in vastly different conditions deep underground, millions of years ago. Intrusions are known to occur in a great variety of sizes and shapes. Some of the most common types are illustrated in Figure 4.26. Notice that some plutons have a tabular shape, whereas others are best described as massive. Also, observe that some of these bodies cut across existing structures, such as sedimentary strata, whereas others form when magma is injected between sedimentary layers. Because of these differences, intrusive igneous bodies are generally classified according to their shape as either tabular or massive, and by their orientation with respect to the host rock. Igneous bodies are said to be discordant. If they cut across existing structures and concordant, discord are equals to. Disagree, if they inject parallel to features such as sedimentary strata. Smart Figure 4.26 Intrusive igneous structures. Smart Figure 4.26 Full alternative text description. Tabular intrusive bodies, dikes and sills. Dikes and sills. Watch animation, intrusive igneous activity. Tabular intrusive bodies are produced when magma is forcibly injected into a fracture or zone of weakness, such as a bedding surface. Dikes are discordant bodies that form when magma is forcibly injected into fractures and cut across bedding surfaces and other structures in the host rock. By contrast, sills are nearly horizontal, concordant bodies that form when magma exploits weaknesses between sedimentary beds or other rock structures. In general, dikes serve as tabular conduits that transport magma upward, whereas sills tend to accumulate magma and increase in thickness. The dark, essentially horizontal band is a sill of basaltic composition that intruded horizontal layers of sedimentary rock. Smart Figure 4.27 Sill exposed in Sinbad County, Utah. Dikes and sills are typically shallow features, occurring where the country rocks are sufficiently brittle to fracture. They can range in thickness from less than 1 mm to more than 1 km. While dikes and sills can occur as solitary bodies, dikes tend to form in roughly parallel groups called dike swarms. These multiple structures reflect the tendency for fractures to form in sets when tensional forces pull apart brittle country rock. Dikes can also radiate from an eroded volcanic neck, like spokes on a wheel. In these situations, the active ascent of magma generated fissures in the volcanic cone, out of which lava flowed. Dikes frequently are more resistant and thus weather more slowly than the surrounding rock. Consequently, when exposed by erosion, dikes tend to have a wall-like appearance, as shown in Figure 4.28. This wall-like dike is composed of igneous rock that is more resistant to weathering than the surrounding material. Watch Mobile Field Trip, Dikes and Sills in the Sinbad Country. Smart Figure 4.28 Dike exposed in the Spanish Peaks, Colorado. Because dikes and sills are relatively uniform in thickness and can extend for many kilometers, they are assumed to be the product of very fluid, and therefore mobile, magmas. One of the largest and most studied of all sills in the United States is the Palisades Sill. Exposed for 80 kilometers along the west bank of the Hudson River in southeastern New York and northeastern New Jersey, this sill is about 300 meters thick. Because it is resistant to erosion, the Palisades Sill forms an imposing cliff that can be easily seen from the opposite side of the Hudson. Watch Condor Video, Intrusive Igneous Bodies. Columnar jointing. In many respects, sills closely resemble buried lava flows. Both are tabular and can extend over a wide area, and both may exhibit columnar jointing. Columnar jointing occurs when igneous rocks cool and develop shrinkage fractures that produce elongated, pillar-like columns that most often have 6 sides. Further, because sills and dikes generally form in near-surface environments and may be only a few meters thick, the eam-placed magma often cools quickly enough to generate a fine-grained texture. Giant's Causeway in Northern Ireland is an excellent example of columnar jointing. Figure 4.29 Columnar jointing. Massive intrusive bodies, batholiths, stalks, and laccoliths. Batholiths and stalks. By far the largest intrusive igneous bodies are batholiths. Batholiths occur as mammoth linear structures several hundred kilometers long and more than 100 kilometers wide. The Sierra Nevada batholith, for example, is a continuous granitic structure that forms much of the backbone of the Sierra Nevada in California. An even larger batholith extends for over 1,800 kilometers along the coast mountains of western Canada and into southern Alaska. Although batholiths can cover a large area, recent geophysical studies indicate that most are less than 10 kilometers thick. Some are even thinner. The coastal batholith of Peru, for example, is essentially a flat slab with an average thickness of only 2 to 3 kilometers. Batholiths are typically composed of felsic and intermediate rock types and are often called granitic batholiths. These gigantic, elongated bodies consist of numerous plutons that were emplaced beginning about 150 million years ago. Figure 4.30 Granitic batholiths along the western margin of North America. Figure 4.30 Full alternative text description. Early investigators thought the Sierra Nevada batholith was a huge single body of intrusive igneous rock. Today we know that large batholiths are produced by hundreds of discrete injections of magma that form smaller intrusive bodies that intimately crowd against or penetrate one another. These bulbous masses are emplaced over spans of millions of years. The intrusive activity that created the Sierra Nevada batholith, for example, occurred nearly continuously over a 130 million year period that ended about 80 million years ago. A batholith is generally defined as a plutonic body having a surface exposure greater than 100 square kilometers. Smaller plutons are termed stalks. However, many stalks appear to be portions of much larger intrusive bodies that would be classified as batholiths if they were fully exposed. Did you know? In the eastern United States, some exposed granitic intrusions have dome-shaped, nearly treeless summits, hence the name summit balds. Examples include Cadillac Mountain in Maine, Mount Chocorua in New Hampshire, Black Mountain in Vermont, and Stone Mountain in Georgia. Laccoliths. A 19th-century study by G. K. Gilbert of the U.S. Geological Survey in the Henry Mountains of Utah produced the first clear evidence that igneous intrusions can lift the sedimentary strata they penetrate. Gilbert named the igneous intrusions he observed laccoliths, which he envisioned as igneous rock forcibly injected between sedimentary strata, so as to arch the beds above while leaving those below relatively flat. It is now known that the 5 major peaks of the Henry Mountains are not laccoliths but stalks. However, these central magma bodies are the source material for branching offshoots that are true laccoliths, as Gilbert defined them. Mount Ellen in Utah's Henry Mountains is one of 5 peaks that make up this small mountain range. Although the main intrusions in the Henry Mountains are stalks, numerous laccoliths formed as offshoots of these structures. Figure 4.31 Laccoliths. Numerous other granitic laccoliths have since been identified in Utah. The largest is a part of the Pine Valley Mountains located north of St. George, Utah. Others are found in the La Salle Mountains near Arches National Park and in the Abajo Mountains directly to the south. Concept checks 4.8. 1. What is meant by the term country rock? 2. Describe dikes and sills, using the appropriate terms from the following list: massive, discordant, tabular, and concordant. 3. Distinguish among batholiths, stalks, and laccoliths in terms of size and shape. 4.9 Mineral resources and igneous processes. Explain how economic deposits of gold, silver, and many other metals form. Given the growth of the middle class in countries such as China, India, and Brazil, the demand for metallic natural resources has increased exponentially in recent years. Some of the most important accumulations of metals, such as gold, silver, copper, mercury, lead, platinum, and nickel, are produced by igneous processes. These mineral resources result from processes that concentrate desirable materials to the point where they can be profitably extracted. Therefore, knowledge of how and where these important materials are likely to be concentrated is vital to our well-being. Table 4.1 Occurrences of metallic minerals. Table 4.1 Full alternative text description. Magmatic differentiation and/or deposits. The igneous processes that generate some important metal deposits are quite straightforward. For example, as a large basaltic magma body cools, the heavy minerals that crystallize early tend to settle to the lower portion of the magma chamber. This type of magmatic differentiation serves to concentrate some metals, producing major deposits of chromite, magnetite, and platinum. Layers of chromite, interbedded with other heavy minerals, are mined at Montana's Stillwater Complex, whereas the Bushveld Complex in South Africa contains over 70% of the world's known reserves of platinum. Pegmatite deposits. Magmatic differentiation during the late stages of the magmatic process is important in producing ores. This is particularly true of granitic magmas, in which the residual melt can become enriched in rare elements, including some heavy metals. Further, because water and other volatile substances do not crystallize along with the bulk of the magma body, these fluids make up a high percentage of the melt during the final phase of cooling and solidification. Crystallization in a fluid-rich environment, where ion migration is enhanced, results in the formation of crystals several centimeters, or even a few meters, in length. The resulting rocks, called pegmatites, are composed of these unusually large crystals. This granite pegmatite, found in the inner gorge of the Grand Canyon, is composed mainly of quartz and feldspar. Figure 4.32 Pegmatite. Feldspar masses the size of houses have been quarried from a pegmatite located in North Carolina. Gigantic hexagonal crystals of muscovite measuring a few meters across have been found in Ontario, Canada. In the Black Hills, spodumene crystals as thick as telephone poles have been mined. The largest of these was more than 12 meters long. Not all pegmatites contain such large crystals, but these examples emphasize the special conditions that must exist during their formation. Most pegmatites are granitic in composition and consist of unusually large crystals of quartz, feldspar, and muscovite. Feldspar is used in the production of ceramics, and muscovite is used for electrical insulation and glitter. Further, pegmatites often contain some of the least abundant elements. Minerals containing the elements lithium, cesium, uranium, and the rare earths are occasionally found. Moreover, some pegmatites contain semi-precious gems such as beryl, topaz, and tourmaline. Most pegmatites are located within large igneous masses, or as dikes or veins that cut into the host rock that surrounds the magma chamber. Illustration of the relationship between an igneous body and associated pegmatites and hydrothermal mineral deposits. Smart Figure 4.33 Full alternative text description. Not all late-stage magmas produce pegmatites, nor do all have a granitic composition. Some magmas instead become enriched in iron or occasionally copper. For example, at Kiruna, Sweden, magma composed of over 60% magnetite solidified to produce one of the largest iron deposits in the world. Smart Figure 4.33 Pegmatites and hydrothermal deposits. Watch tutorial, Hydrothermal deposits. Hydrothermal deposits. Among the best-known and most important ore deposits are those generated from hot, ion-rich fluids called hydrothermal solutions. Included in this group are the gold deposits of the Homestake Mine in South Dakota, the lead, zinc, and silver ores near Coeur d'Alene, Idaho, the silver deposits of the Comstock Lode in Nevada, and the copper ores of Michigan's Keweenaw Peninsula. Because these hot, ion-rich fluids tend to chemically alter the host rock, this process is called hydrothermal metamorphism, and it is discussed in Chapter 8. Hydrothermal vein deposits. The majority of hydrothermal deposits originate from hot, metal-rich fluids that are remnants of late-stage magmatic processes. During the cooling process, liquids plus various metallic ions accumulate near the top of the magma chamber. Because of their mobility, these ion-rich solutions can migrate great distances through the surrounding rock before they are eventually deposited, usually as sulfides of various metals. Some of these fluids move along openings such as fractures or bedding planes, where they cool and precipitate metallic ions to produce vein deposits. Many of the most productive deposits of gold, silver, copper, and mercury occur as hydrothermal vein deposits. This nearly pure metal from northern Michigan's Keweenaw Peninsula is an excellent example of a hydrothermal deposit. This area was once an important source of copper that is now largely depleted. Disseminated deposits. Figure 4.34 Native copper. Another important type of accumulation generated by hydrothermal activity is called a disseminated deposit. Rather than being concentrated in narrow veins and dikes, these ores are distributed as minute masses throughout the entire rock mass. Much of the world's copper is extracted from disseminated deposits, including those at Chuquicamata, Chile, and the huge Bingham Canyon copper mine in Utah. Because these accumulations contain only 0.4 to 0.8% copper, between 125 and 250 kilograms of ore must be mined for every 1 kilogram of metal recovered. The environmental impact of these large excavations is significant and includes problems related to waste disposal. Origin of diamonds. An economically important mineral with an igneous origin is diamond. Although best known as gems, diamonds are used extensively as abrasives. Diamonds are thought to originate at depths of nearly 200 kilometers, where the confining pressure is great enough to generate this high-pressure form of carbon. Once crystallized, the diamonds are carried upward through pipe-shaped conduits that increase in diameter toward the surface. In diamond-bearing pipes, nearly the entire pipe contains diamond crystals that are disseminated throughout an ultramafic rock called kimberlite. The most productive kimberlite pipes are those in South Africa. The only equivalent source of diamonds in the United States is located near Murfreesboro, Arkansas, but several attempts at commercial diamond mining at this location failed. In 1972, the state of Arkansas purchased the property and developed it into Crater of Diamonds State Park. Park visitors are encouraged to hunt for diamonds and can keep what they find. Did you know? Although the United States is the largest consumer of industrial diamonds, it has no commercial source of this mineral. It does, however, manufacture large quantities of synthetic diamonds for industrial use. Concept checks 4.9. 1. Name and compare two types of hydrothermal deposits. 2. In what type of environment are pegmatites produced? Concepts in review: igneous rocks and intrusive activity. 4.1 Magma, parent material of igneous rock. List and describe the three major components of magma. Key terms: igneous rock, magma, lava, melt, volatile crystallization. Intrusive igneous rock, extrusive igneous rock. Completely or partly molten rock is called magma if it is below Earth's surface, and lava if it has erupted onto the surface. It consists of a liquid melt that may also contain solid mineral crystals and gases, such as water vapor or carbon dioxide. As magma cools, silicate minerals begin to form from the cocktail of mobile ions in the melt. These tiny crystals grow through the addition of ions to their outer surface. As cooling proceeds, crystallization gradually transforms the magma into a solid mass of interlocking crystals, an igneous rock. Magmas that cool below the surface produce intrusive igneous rocks, whereas those that erupt onto Earth's surface produce extrusive igneous rocks. 4.2 Igneous compositions. Compare and contrast the four basic igneous compositions: felsic, intermediate, mafic, and ultramafic. Key terms: felsic composition, mafic composition, intermediate composition. Peridotite, ultramafic. Igneous rocks are composed mostly of silicate minerals. Igneous rocks that are composed mostly of light-colored silicate minerals are described as having a felsic composition. Rocks composed of greater than 45% ferromagnesian minerals are classified as mafic. Mafic rocks are generally darker in color and more dense than their felsic counterparts. Broadly, continental crust is felsic in composition, and oceanic crust is mafic. Intermediate rocks in which plagioclase feldspar predominates have a composition that is intermediate between felsic and mafic. They are typical of continental volcanic arcs. Ultramafic rocks, which are rich in the minerals olivine and pyroxene, dominate the upper mantle. The amount of silica in an igneous rock is an indication of its overall composition. Rocks that are rich in silica are felsic, while rocks that are poor in silica are mafic or ultramafic. The amount of silica present in a magma determines the magma's viscosity and crystallization temperature. Describe igneous rocks having the compositions of samples A and D using terms such as mafic, felsic, etc. Would you ever expect to find quartz and olivine in the same rock? Why or why not? Figure 4.11-1 Full alternative text description. 4.3 Igneous textures, what can they tell us? Identify and describe the 6 major igneous textures. Key terms. Texture. Aphanitic. Phaneritic porphyritic texture. Phenocryst ground mass. Porphyry vesicular texture. Glassy texture. Pyroclastic texture. To geologists, texture is a description of the size, shape, and arrangement of mineral grains in a rock. Careful observation of the texture of igneous rocks can tell us about the conditions under which they formed. The rate at which magma or lava cools is an important factor in the rock's final texture. Lava cools quickly at or close to the surface, so crystallization is rapid and results in a large number of very small crystals. The result is a fine-grained texture. Magma cooling at depth loses heat more slowly. This allows sufficient time for the magma's ions to be organized into larger crystals, resulting in a rock with a coarse-grained texture. If crystals begin to form at depth and then the magma moves to a shallow depth or erupts at the surface, it will have a 2-stage cooling history. The result is a rock with a porphyritic texture. Volcanic rocks may exhibit additional textures: vesicular if the lava had a high gas content, glassy if it was high in silica, or pyroclastic if the lava erupted explosively. 4.4 Naming igneous rocks. Distinguish among the common igneous rocks based on texture and mineral composition. Key terms. Granite, rhyolite, obsidian, pumice, andesite, diorite, basalt, gabbro, pyroclastic rock. Igneous rocks are classified on the basis of their textures and compositions. Figure 4.12 summarizes the naming system based on these 2 criteria. 2 magmas with the same composition can cool at different rates, resulting in different final textures. On the other hand, 2 magmas that have different compositions may attain similar textures if they cool under similar circumstances. Is it possible for granite to be transformed into rhyolite? If so, what processes would have to be involved? 4.5 Origin of magma. Summarize the major processes that generate magma from solid rock. Key terms. Geothermal gradient, decompression, melting. Solid rock may melt under 3 geologic circumstances: when heat is added to the rock, raising its temperature, when already hot rock experiences lower pressures, and when water is added. Different processes produce magma in various tectonic settings. Consider situations A, B, and C in the diagram and describe the processes that would be most likely to trigger melting in each. 4.6 How magmas evolve. Describe how magmatic differentiation can generate a magma body that has a mineralogy that is different from its parent magma. Key terms. Bowen's reaction series, crystal settling. Magmatic differentiation assimilation magma mixing. Pioneering experimentation by N.L. Bowen revealed that in a cooling magma, minerals crystallize in a specific order. Ferromagnesian silicates such as olivine crystallize first, at the highest temperatures, and non-ferromagnesian silicates such as quartz crystallize last, at the lowest temperatures. Bowen found that in between these temperatures, chemical reactions take place between the crystallized silicates and the melt, resulting in compositional changes to each and the formation of new minerals. Various physical processes can cause changes in the composition of magma. For instance, if crystallized silicates are denser than the remaining magma, they will sink to the bottom of the magma chamber. Because these early formed minerals are likely to be ferromagnesian, the magma has now differentiated toward a more felsic composition. As they migrate, magmas may assimilate fragments of their host rocks or mix with other magma bodies. These processes will alter the magma's composition. Consider the accompanying diagram, which shows a cross-sectional view of a hypothetical magma chamber. Using your understanding of Bowen's reaction series and magma evolution, interpret the layered structure by explaining how crystallization occurred. 4.7 Partial melting and magma composition. Describe how partial melting of the mantle rock peridotite can generate a basaltic magma. Key terms. Partial melting. In most circumstances, when rocks melt, they do not melt completely. Different minerals have different temperatures at which they change state from solid to liquid. As rocks melt, minerals with the lowest melting temperatures melt first. Partial melting of the ultramafic mantle yields mafic oceanic crust. Partial melting of the lower continental crust at subduction zones produces magmas that have intermediate or felsic compositions. How is partial melting important for generating the different kinds of igneous rocks found on Earth? 4.8 Intrusive igneous activity. Compare and contrast these intrusive igneous structures, dikes, sills, batholiths, stocks, and laccoliths. Key terms. Host rock intrusion tabular massive discordant concordant dike sill. Columnar jointing batholith stock laccolith. When magma intrudes other rocks, it may cool and crystallize before reaching the surface to produce intrusions called plutons. Plutons come in many shapes. They may cut across the host rocks without regard for pre-existing structures, or the magma may flow along weak zones in the host rock, such as between the horizontal layers of sedimentary bedding. Tabular intrusions may be concordant or discordant. Massive plutons may be small or very large. A blister-like intrusion that lifts the overlying rock layers is a laccolith. As solid igneous rock cools, its volume decreases. Contraction can produce a distinctive fracture pattern called columnar jointing. Label the intrusive igneous structures in the accompanying diagram using the following terms: volcanic neck, sill, batholith, laccolith. Figure 4.11-1 Full alternative text description. 4.9 Mineral resources and igneous processes. Explain how economic deposits of gold, silver, and many other metals form. Key terms. Pegmatite vein deposit, disseminated deposit. Some of the most important accumulations of metallic resources, such as gold, silver, lead, and copper, are produced by igneous processes. Magmatic differentiation can concentrate some metals, producing major deposits. Crystallization in a fluid-rich environment, where ion migration is enhanced, results in the formation of unusually large crystals. The resulting rocks, which may become enriched in rare elements and metals, such as gold and silver, are called pegmatites. The best-known ore deposits are generated from hydrothermal solutions. Many hydrothermal deposits originate from hot, metal-rich fluids that are remnants of late-stage magmatic processes. Hydrothermal solutions move along fractures or bedding planes, cool, and precipitate the metallic ions to produce vein deposits. In a disseminated deposit, the ores from hydrothermal solutions are distributed as minute masses throughout the entire rock mass. Give it some thought. 1. Would you expect all the crystals in an intrusive igneous rock to be the same size? Explain why or why not. 2. Apply your understanding of igneous rock textures to describe the cooling history of each of the igneous rocks pictured here. 3. Use figure 4.5 to classify the following igneous rocks. A. An aphanitic rock containing about 30% calcium-rich plagioclase feldspar, 55% pyroxene, and 15% olivine. B. A phaneritic rock containing about 20% quartz, 40% potassium feldspar, 20% sodium-rich plagioclase feldspar, a few percent muscovite, and the remainder dark-colored silicate. C. An aphanitic rock containing about 50% plagioclase feldspar, 35% amphibole, 10% pyroxene, and minor amounts of other light-colored silicates. D. A phaneritic rock made mainly of olivine and pyroxene, with lesser amounts of calcium-rich plagioclase feldspar 4. Identify the igneous rock textures described by each of the following statements. A. Openings produced by escaping gases. B. The texture of obsidian. C. A matrix of fine crystals surrounding phenocrysts. D. Consists of crystals that are too small to be seen without a microscope. E. A texture characterized by rock fragments welded together. F. Coarse-grained, with crystals of roughly equal size. 5. During a hike, you pick up the igneous rock shown in the accompanying photo. A. What is the mineral name of the small, rounded, glassy green crystals? B. Did the magma from which this rock formed likely originate in the mantle or in the crust? Explain. C. Was the magma likely a high-temperature magma or a low-temperature magma? Explain. D. Describe the texture of this rock. 6. A common misconception about Earth's upper mantle is that it is a thick shell of molten rock. Explain why Earth's mantle is actually solid under most conditions. 7. Describe 2 mechanisms by which mantle rock can melt without an increase in temperature. How do these magma-generating mechanisms relate to plate tectonics? 8. Use your understanding of Bowen's reaction series to explain how partial melting can generate magmas that have different compositions. 9. During a field trip with your geology class, you visit an exposure of rock layers similar to the one sketched here. A fellow student suggests that the layer of basalt is a sill, but you disagree. Why do you think the other student is incorrect? What is a more likely explanation for the basalt layer? 10. Each of the following statements describes how an intrusive feature appears when exposed to Earth's surface due to erosion. Name each feature. A. A dome-shaped mountainous structure flanked by upturned layers of sedimentary rocks. B. A vertical wall-like feature a few meters wide and hundreds of meters long. C. A huge expanse of granitic rock forming a mountainous terrain tens of kilometers wide. D. A relatively thin layer of basalt sandwiched between horizontal layers of sedimentary rocks exposed along the walls of a river valley. 11. Mount Whitney, the highest summit in the contiguous United States, is located in the Sierra Nevada batholith. Based on its location, is Mount Whitney likely composed mainly of granitic, andesitic, or basaltic rocks? Mastering Geology trademark. Looking for additional review and test prep materials? Visit the study area in Mastering Geology to enhance your understanding of this chapter's content by accessing a variety of resources, including self-study quizzes, geoscience animations, smart figures, mobile field trips, Project Condor quadcopter videos, and the news RSS feeds, flashcards, web links, and an optional Pearson e-text. Chapter 5: Volcanoes and Volcanic Hazards. Revendedor ejecting volcanic bombs and incandescent ash at night, November 2015. This volcano, which is located in the Andes of Ecuador, has erupted more than 25 times since 1541. Focus on concepts. Each statement represents the primary learning objective for the corresponding major heading within the chapter. After you complete the chapter, you should be able to 5.1 Compare and contrast the 1980 eruption of Mount St. Helens with the most recent eruption of Kilauea, which began in 1983. 5.2 Explain why some volcanic eruptions are explosive and others are quiescent. 5.3 List and describe the three categories of materials extruded during volcanic eruptions. 5.4 Draw and label a diagram that illustrates the basic features of a typical volcanic cone. 5.5 Summarize the characteristics of shield volcanoes and provide one example of this type of volcano. 5.6 Describe the formation, size, and composition of cinder cones. 5.7 List the characteristics of composite volcanoes and describe how they form. 5.8 Describe the major geologic hazards associated with volcanoes. 5.9 List volcanic landforms other than shield, cinder cone, and composite volcanoes and describe their formation. 5.10 Explain how the global distribution of volcanic activity is related to plate tectonics. The significance of igneous activity may not be obvious at first glance. However, because volcanoes extrude molten rock that formed at great depth, they provide our only means of directly observing processes that occur many kilometers below Earth's surface. Furthermore, Earth's atmosphere and oceans have evolved from gases emitted during volcanic eruptions. Either of these facts is reason enough for igneous activity to warrant our attention. 5.1 Mount St. Helens versus Kilauea. Compare and contrast the 1980 eruption of Mount St. Helens with the most recent eruption of Kilauea, which began in 1983. On May 18, 1980, the largest volcanic eruption to occur in North America in historic times transformed a picturesque volcano into a decapitated remnant. On that date in southwestern Washington state, Mount St. Helens erupted with tremendous force. The blast blew out the entire north flank of the volcano, leaving a gaping hole. In one brief moment, a prominent volcano whose summit had been more than 2,900 meters above sea level was lowered by more than 400 meters. Figure 5.1 Before and after photographs show the transformation of Mount St. Helens. The May 18, 1980, eruption of Mount St. Helens occurred in southwestern Washington. Figure 5.1 Full alternative text description. The event devastated a wide swath of timber-rich land on the north side of the mountain. Trees within a 400 square kilometer area lay intertwined and flattened, stripped of their branches and appearing from the air like toothpicks strewn about. The accompanying mud flows carried ash, trees, and water-saturated rock debris 29 kilometers down the Toutle River. The eruption claimed 59 lives, some died from the intense heat and the suffocating cloud of ash and gases, others from the impact of the blast, and still others from being trapped in mud flows. Figure 5.2 Douglas fir trees snapped off or uprooted by the lateral blast of Mount St. Helens. The eruption ejected nearly a cubic kilometer of ash and rock debris. Following the devastating explosion, Mount St. Helens continued to emit great quantities of hot gases and ash. The force of the blast was so strong that some ash was propelled more than 18 kilometers into the stratosphere. During the next few days, this very fine-grained material was carried around Earth by strong upper-air winds. Crops were damaged in central Montana, and measurable deposits were reported as far away as Oklahoma and Minnesota. Meanwhile, ash fallout in the immediate vicinity exceeded 2 meters in depth. The air over Yakima, Washington, was so filled with ash that residents experienced midnight-like darkness at noon. Not all volcanic eruptions are as violent as the 1980 Mount St. Helens event. Some volcanoes, such as Hawaii's Kilauea volcano, generate relatively quiet outpourings of fluid lavas. These quiescent eruptions are not without some fiery displays. Occasionally fountains of incandescent lava spray hundreds of meters into the air, but most lava pours from the vent and flows downslope. During Kilauea's most recent active phase, which began in 1983, more than 180 homes in a national park visitor center have been destroyed by flowing lava igniting material in its path. Testimony to the quiescent nature of Kilauea's eruptions is the fact that the Hawaiian Volcanoes Observatory has operated on its summit since 1912, despite the fact that Kilauea has had more than 50 eruptive phases since record-keeping began in 1823. Did you know? The eruption of Tambora, in Indonesia, in 1815 is the largest known volcanic event in modern history. About 20 times more ash and rock were explosively ejected during this eruption than were emitted during the 1980 Mount St. Helens event. The sound of the explosion was heard an incredible 4,800 kilometers away, about the distance across the conterminous United States. Concept checks 5.1. 1. Briefly compare the 1980 eruption of Mount St. Helens to a typical eruption of Hawaii's Kilauea volcano. 5.2. The nature of volcanic eruptions. Explain why some volcanic eruptions are explosive and others are quiescent. Volcanic activity is commonly perceived as a process that produces a picturesque, cone-shaped structure that periodically erupts in a violent manner. However, many eruptions are not explosive, as indicated by Kilauea's activity. What determines the manner in which volcanoes erupt? Magma, source material for volcanic eruptions. Recall that magma, molten rock that may contain some solid crystalline material and also contains varying amounts of dissolved gas, is the parent material of igneous rocks. Erupted magma is called lava. Composition of magma. As we discussed in Chapter 4, mafic igneous rocks contain a high percentage of dark silicate minerals and calcium-rich plagioclase feldspar, and as a result, they tend to be dark in color. By contrast, felsic rocks contain mainly light-colored silicate minerals, quartz and potassium feldspar. Intermediate rocks have a composition between mafic and felsic rocks. Correspondingly, mafic magmas contain a much lower percentage of silica than do felsic magmas. The compositional differences between magmas also affect several other properties, as summarized in Figure 5. 3. As shown in Figure 5.3, mafic magmas have the lowest silica content and the lowest gas content, and they erupt at the highest temperatures. By contrast, felsic magmas have the highest silica content and the highest gas content, and they erupt at the lowest temperatures. Intermediate magmas have characteristics between mafic and felsic magmas. Figure 5.3 compositional differences of magma bodies cause their properties to vary. Figure 5.3 Full alternative text description. Where is magma generated? Recall that most magma is generated in Earth's upper mantle by partial melting of solid rock. The magmas generated by melting mantle rocks tend to have basaltic composition. Once formed, basaltic magma, which is less dense than the surrounding rocks, slowly rises toward Earth's surface. In some settings, this hot molten rock reaches the surface, where it usually produces fluid outflows of basaltic lavas. As a result of seafloor spreading, the largest quantity of basaltic magma erupts on the ocean floor along divergent plate boundaries. Extensive basaltic flows are also the product of hotspot volcanism generated by rising hot mantle plumes. In continental settings, however, overlying crustal rocks are usually less dense than the ascending basaltic magma, and as a result, the rising molten rock ponds at the crust mantle boundary. Because the newly formed magma is much hotter than the melting temperature of crustal rocks, the rocks overlying the magma body begin to melt. This process generates a less dense, more silica-rich magma of intermediate or felsic composition, which then continues the journey toward Earth's surface. Effusive versus explosive eruptions. Volcanic eruptions exhibit a range of behavior from quiescent eruptions that produce outpourings of fluid lava to explosive eruptions. Geologists often refer to quiescent eruptions as effusive eruptions. The two primary factors that determine how magma erupts are its viscosity and gas content. Viscosity is a measure of a fluid's mobility. The more viscous a material, the greater its resistance to flow. For example, pancake syrup is more viscous, and thus more resistant to flow, than water. Factors affecting viscosity. Magma's viscosity depends primarily on its temperature and silica content. The more silica in magma, the greater its viscosity. Silicate structures begin to link together into long chains early in the crystallization process, which makes the magma more rigid and impedes its flow. Consequently, silica-rich felsic lavas are the most viscous and tend to travel at imperceptibly slow speeds to form comparatively short, thick flows. By contrast, mafic lavas, which contain much less silica, are relatively fluid and have been known to travel 150 kilometers or more before solidifying. Intermediate magmas have flow rates between these extremes. Temperature affects the viscosity of magma in much the same way it affects the viscosity of pancake syrup. The hotter a magma, the more fluid it will be. As lava cools and begins to congeal, its viscosity increases, and the flow eventually halts. Role of gases. The nature of volcanic eruptions also depends on the amount of dissolved gases held in the magma body by the pressure exerted by the overlying rock. The most abundant gases in most magmas are water vapor and carbon dioxide. These dissolved gases tend to come out of solution when the confining pressure is reduced. This is analogous to how carbon dioxide is retained in cans and bottles of soft drinks. When the pressure is reduced on a soft drink by opening the cap, the dissolved carbon dioxide quickly separates from the solution to form bubbles that rise and escape. The viscosity and gas content of magma are directly related to its composition, as shown in Figure 5. 3. At one end of the spectrum are basaltic magmas, which are very fluid and have a low gas content, sometimes as little as 0.5% by weight. At the other extreme are rhyolitic magmas, which are highly viscous and contain a lot of gas, as much as 8% by weight. Effusive Hawaiian-type eruptions. All magmas contain some water vapor and other gases that are kept in solution by the immense pressure of the overlying rock. As magma rises, the confining pressure drops, causing the dissolved gases to separate from the melt and form large numbers of tiny bubbles. When fluid basaltic magmas erupt, these pressurized gases readily escape. At temperatures that often exceed 1,100 degrees Celsius, these gases can quickly expand to occupy hundreds of times their original volumes. Occasionally, these expanding gases propel incandescent lava hundreds of meters into the air, producing lava fountains. Although spectacular, these fountains are usually harmless and generally not associated with major explosive events that cause great loss of life and property. Figure 5.4 Lava fountain produced by gases escaping fluid basaltic lava. Kilauea, on Hawaii's Big Island, is one of the most active volcanoes on Earth. Eruptions that involve very fluid basaltic lavas, such as the recent eruptions of Kilauea on Hawaii's Big Island, are often triggered by the arrival of a new batch of molten rock, which accumulates in a near-surface magma chamber. Geologists can usually detect such an event because the summit of the volcano begins to inflate and rise months or even years before an eruption. The injection of a fresh supply of hot molten rock heats and remobilizes the semi-liquid magma in the chamber. In addition, swelling of the magma chamber fractures the rock above, allowing the fluid magma to move upward along the newly formed fissures, often generating effusions of fluid lava for weeks, months, or possibly years. The eruption of Kilauea that began in 1983 is ongoing. How explosive eruptions are triggered. Recall that silica-rich rhyolitic magmas have a relatively high gas content and are quite viscous compared to basaltic magmas. As rhyolitic magma rises, the gases remain dissolved until the confining pressure drops sufficiently, at which time tiny bubbles begin to form and increase in size. Because of the high viscosity of rhyolitic magma, gas bubbles tend to remain trapped in the magma, forming a sticky froth. When the pressure exerted by the expanding magma exceeds the strength of the overlying rock, fracturing occurs. As the frothy magma moves up through the fractures, a further drop in confining pressure creates additional gas bubbles. This chain reaction often generates an explosive event in which magma is literally blown into fragments that are carried to great heights by the escaping hot gases. When molten rock in the uppermost portion of the magma chamber is forcefully ejected by the escaping gases, the confining pressure on the magma directly below also drops suddenly. Thus, rather than being a single bang, an explosive eruption is really a series of violent explosions that can last for a few days. Because highly gaseous magmas expel fragmented lava at nearly supersonic speeds, they are associated with hot, buoyant eruption columns consisting mainly of volcanic ash and gases. Eruption columns can rise perhaps 40 kilometers into the atmosphere. It is not uncommon for a portion of an eruption column to collapse, sending hot ash rushing down the volcanic slope at speeds exceeding 100 kilometers per hour. As a result, volcanoes that erupt highly viscous magmas having a high gas content are the most destructive to property and human life. Steam and ash eruption column from Mount Sinabung, Indonesia, 2014. A deadly cloud of fiery ash can be seen racing down the volcano slope in the foreground. Smart Figure 5.5 eruption column generated by viscous, silica-rich magma. Following explosive eruptions, partially degassed lava may slowly ooze out of the vent to form thick lava flows or dome-shaped lava bodies that grow over the vent. Watch video, Eruption Columns. Concept Checks 5.2. 1. List these magmas in order, from the most silica-rich to the least silica-rich: mafic magma, felsic magma, intermediate magma. 2. List the two primary factors that determine the manner in which magma erupts. 3. Define viscosity. 4. Are volcanoes fed by highly viscous magma more or less likely to be a greater threat to life and property than volcanoes supplied with very fluid magma? 5.3 Materials extruded during an eruption. List and describe the three categories of materials extruded during volcanic eruptions. Volcanoes erupt lava, large volumes of gas, and pyroclastic materials. In this section we will examine each of these materials. Lava flows. The vast majority of Earth's lava, more than 90% of the total volume, is estimated to be mafic in composition. Most of mafic lavas erupt on the seafloor via a process known as submarine volcanism. Lavas having an intermediate composition account for most of the rest, while felsic flows make up as little as 1% of the total. Rhyolitic magmas tend to extrude mostly volcanic ash rather than lava. On land, hot basaltic lavas, which are usually very fluid, generally flow in thin, broad sheets or stream-like ribbons. Fluid basaltic lavas have been clocked at speeds exceeding 30 km per hour down steep slopes. However, flow rates of 10 to 300 meters per hour are more common. Silica-rich rhyolitic lava, by contrast, often moves too slowly to be perceived. Furthermore, rhyolitic lavas seldom travel more than a few kilometers from their vents. As you might expect, andesitic lavas, which are intermediate in composition, exhibit flow characteristics between these extremes. AA and Pahoehoe flows. Fluid basaltic magmas tend to generate two types of lava flows, which are known by their Hawaiian names. The first, called AA flows, have surfaces of rough jagged blocks with dangerously sharp edges and spiny projections. Crossing a hardened AA flow can be a trying and miserable experience. The second type, Pahoehoe flows, exhibit smooth surfaces that sometimes resemble twisted braids of ropes. A slow-moving, basaltic AA flow advancing over hardened Pahoehoe lava. B, a typical fluid Pahoehoe lava. Both of these lava flows erupted from a rift on the flank of Hawaii's Kilauea volcano. Figure. .6 Full alternative text description. Although both lava types can erupt from the same volcano, Pahoehoe lavas are hotter and more fluid than AA flows. In addition, Pahoehoe lavas can change into AA lava flows, although the reverse does not occur. Figure 5.6 Lava flows. Cooling that occurs as the flow moves away from the vent is one factor that facilitates the change from Pahoehoe to AA. The lower temperature increases viscosity and promotes bubble formation. Escaping gas bubbles produce numerous voids and sharp spines in the surface of the congealing lava. As the molten interior advances, the outer crust is broken, transforming the relatively smooth surface of a Pahoehoe flow into an AA flow made up of an advancing mass of rough, sharp, broken lava blocks. Pahoehoe flows often develop cave-like tunnels called lava tubes that start as conduits for carrying lava from an active vent to the flow's leading edge. Lava tubes form in the interior of a lava flow, where the temperature remains high long after the exposed surface cools and hardens. Because they serve as insulated pathways that allow lava to flow great distances from its source, lava tubes are important features of fluid lava flows. A lava flow may develop a solid upper crust, while the molten lava below continues to advance in a conduit called a lava tube. Some lava tubes exhibit extraordinary dimensions. Kazumura Cave, located on the southeastern slope of Hawaii's Mauna Loa volcano, is a lava tube extending more than 60 kilometers. B. The collapsed section of the roof of a lava tunnel results in a skylight. Figure 5.7 Lava tubes. Figure 5.7 Full alternative text description. Pillow lavas. Recall that most of Earth's volcanic output occurs along oceanic ridges, generating new oceanic crust. When outpourings of lava occur on the ocean floor, the flow's outer skin quickly freezes to form volcanic glass. However, the interior lava is able to move forward by breaking through the hardened surface. This process occurs over and over as molten basalt is extruded like toothpaste from a tightly squeezed tube. The result is a lava flow composed of numerous tube-like structures called pillow lavas, stacked one atop the other. Pillow lavas are useful when reconstructing geologic history because their presence indicates that the lava flow formed below the surface of a water body. These diagrams show the formation of pillow lava. The pillows tend to be elongated tube-like structures and are often variable in shape. The photo shows an undersea pillow lava flow off the coast of Hawaii. Figure 5.8 Full alternative text description. Block lavas. Figure 5.8 Pillow lava. In contrast to fluid basaltic magmas that can travel many kilometers, viscous andesitic and rhyolitic magmas tend to generate relatively short prominent flows, a few hundred meters to a few kilometers long. Their upper surface consists largely of massive, detached blocks, hence the name block lava. Although similar to AA flows, these lavas consist of blocks with slightly curved, smooth surfaces rather than the rough, sharp, spiny surfaces typical of AA flows. Gases. Recall that magmas contain varying amounts of dissolved gases, called volatiles. These gases are held in the molten rock by confining pressure, just as carbon dioxide is held in cans of soft drinks. As with soft drinks, as soon as the pressure is reduced, the gases begin to escape. Obtaining gas samples from an erupting volcano is difficult and dangerous, so geologists usually must estimate the amount of gas originally contained in the magma. The gaseous portion of most magma bodies ranges from less than 1% to about 8% of the total weight, with most of this in the form of water vapor. Although the percentage may be small, the actual quantity of emitted gas can exceed thousands of tons per day. Occasionally, eruptions emit colossal amounts of volcanic gases that rise high into the atmosphere, where they may reside for several years. The composition of volcanic gases is important because these gases contribute significantly to our planet's atmosphere. The most abundant gas typically released into the atmosphere from volcanoes is water vapor, followed by carbon dioxide and sulfur dioxide, with lesser amounts of hydrogen sulfide, carbon monoxide, and helium. Sulfur compounds are easily recognized by their pungent odor. Volcanoes are also natural sources of air pollution. Some emit large quantities of sulfur dioxide, which readily combines with atmospheric gases to form toxic sulfuric acid and other sulfate compounds. Pyroclastic materials. When volcanoes erupt energetically, they eject pulverized rock and fragments of lava and glass from the vent. The particles produced, pyroclastic materials, are also called tephra. These fragments range in size from very fine dust and sand-sized volcanic ash to pieces that weigh several tons. Pyroclastic materials are also commonly referred to as tephra. Figure 5.9 Types of pyroclastic materials. Figure 5.9 Full alternative text description. Ash and dust particles are produced when gas-rich viscous magma erupts explosively. As magma moves up in the vent, the gases rapidly expand, generating a melt that resembles the froth that flows from a bottle of champagne. As the hot gases expand explosively, the froth is blown into very fine glassy fragments. When the hot ash falls, the glassy shards often fuse to form a rock called welded tuff. Sheets of this material, as well as ash deposits that later consolidate, cover vast portions of the western United States. Somewhat larger pyroclasts that range in size from small beads to walnuts are known as lapilli, or cinders. Particles larger than 64 millimeters in diameter are called blocks when they are made of hardened lava, and bombs when they are ejected as incandescent lava. Because bombs are semi-molten when ejected, they often take on a streamlined shape as they hurl through the air. Because of their size and weight, bombs and blocks usually fall near the vent. However, they are occasionally propelled great distances. For instance, bombs 6 meters long and weighing about 200 tons were blown 600 meters from the vent during an eruption of the Japanese volcano Osama. Pyroclastic materials can be classified by texture and composition as well as by size. For instance, scoria is the term for vesicular ejecta produced most often during the eruption of basaltic magmas. These black to reddish-brown fragments are generally found in the size range of lapilli and resemble cinders and clinkers produced by furnaces used to smelt iron. Scoria and pumice are volcanic rocks that exhibit a vesicular texture. Vesicles are small holes left by escaping gas bubbles. Figure 5.10 Common vesicular rocks. Figure 5.10 Full alternative text description. By contrast, when magmas with andesitic or rhyolitic compositions erupt explosively, they emit ash and the vesicular rock pumice. Pumice is usually lighter in color and less dense than scoria, and many pumice fragments have so many vesicles that they are light enough to float. Concept checks 5.3. 1. Contrast Pahoehoe and Aa lava flows. 2. How do lava tubes form? 3. List the main gases released during a volcanic eruption. 4. How do volcanic bombs differ from blocks of pyroclastic debris? 5. What is scoria? How is scoria different from pumice? 5.4 Anatomy of a volcano. Draw and label a diagram that illustrates the basic features of a typical volcanic cone. A popular image of a volcano is a solitary, graceful, snow-capped cone, such as Mount Hood in Oregon or Japan's Fujiyama. These picturesque, conical mountains are produced by volcanic activity that occurred intermittently over thousands, or even hundreds of thousands, of years. However, many volcanoes do not fit this image. Cinder cones are quite small and form during a single eruptive phase that lasts a few days to a few years. Alaska's Valley of 10,000 Smokes is a flat-topped ash deposit that blanketed a river valley to a depth of 200 meters. The eruption that produced it lasted less than 60 hours yet emitted more than 20 times more volcanic material than the 1980 Mount St. Helens eruption. Volcanic landforms come in a wide variety of shapes and sizes, and each volcano has a unique eruptive history. Nevertheless, volcanologists have been able to classify volcanic landforms and determine their eruptive patterns. In this section, we will consider the general anatomy of an idealized volcanic cone. We will follow this discussion by exploring the three major types of volcanic cones: shield volcanoes, cinder cones, and composite volcanoes, as well as their associated hazards. Volcanic activity frequently begins when a fissure develops in Earth's crust as magma moves forcefully toward the surface. As the gas-rich magma moves up through a fissure, its path is usually localized into a somewhat pipe-shaped conduit that terminates at a surface opening called a vent. The cone-shaped structure we call a volcanic cone is often created by successive eruptions of lava, pyroclastic material, or frequently a combination of both, often separated by long periods of inactivity. Compare the structure of the typical composite cone shown here to that of a shield volcano and a cinder cone. Smart Figure 5.11 Anatomy of a volcano. Smart Figure 5.11 Full Alternative Text Description Watch Tutorial, Anatomy of a Volcano. Located at the summit of most volcanic cones is a somewhat funnel-shaped depression called a crater. Volcanoes built primarily of pyroclastic materials typically have craters that form by gradual accumulation of volcanic debris on the surrounding rim. Other craters form during explosive eruptions, as the rapidly ejected particles erode the crater walls. Craters also form when the summit area of a volcano collapses following an eruption. Some volcanoes have very large circular depressions, called calderas, which have diameters that are greater than 1 kilometer, and that in rare cases exceed 50 kilometers. The formation of various types of calderas will be considered later in this chapter. During early stages of growth, most volcanic discharges come from a central summit vent. As a volcano matures, material also tends to be emitted from fissures that develop along the flanks or at the base of the volcano. Continued activity from a flank eruption may produce one or more small parasitic cones. Italy's Mount Etna, for example, has more than 200 secondary vents, some of which have built parasitic cones. Many of these vents, however, emit only gases and are appropriately called fumaroles. Did you know? Chile, Peru, and Ecuador boast the highest volcanoes in the world. Dozens of cones exceed 6,000 m. Two volcanoes located in Ecuador, Chimborazo and Cotopaxi, were once considered the world's highest mountains. That distinction remained until the Himalayas were surveyed in the 19th century. Concept checks 5.4. 1. Distinguish among a conduit, a vent, and a crater. 2. How is a crater different from a caldera? 3. What is a parasitic cone, and where does it form? 4. What is emitted from a fumarole? 5.5 Shield volcanoes. Summarize the characteristics of shield volcanoes and provide one example of this type of volcano. Shield volcanoes are produced by the accumulation of fluid basaltic lavas and exhibit the shape of a broad, slightly domed structure that resembles a warrior's shield. Most shield volcanoes begin on the ocean floor as seamounts, and a few of them grow large enough to form volcanic islands. In fact, many oceanic islands are either a single shield volcano or, more often, the coalescence of two or more shields built upon massive amounts of pillow lavas. Examples include the Hawaiian Islands, the Canary Islands, Iceland, the Galapagos Islands, and Easter Island. Although less common, some shield volcanoes form on continental crust. Included in this group are Nyamiradra, Africa's most active volcano, and Newberry Volcano, Oregon. Figure 5.12 Volcanoes of Hawaii. Mauna Loa, Earth's largest volcano, is one of 5 shield volcanoes that collectively make up the Big Island of Hawaii. Shield volcanoes are built primarily of fluid basaltic lava flows and contain only a small percentage of pyroclastic materials. Figure 5.12 Full alternative text description. Mauna Loa, Earth's largest shield volcano. Extensive study of the Hawaiian Islands has revealed that they are constructed of a myriad of thin basaltic lava flows, each averaging a few meters thick, intermixed with relatively minor amounts of ejected pyroclastic material. Mauna Loa is the largest of 5 overlapping shield volcanoes that comprise the Big Island of Hawaii. From its base on the floor of the Pacific Ocean to its summit, Mauna Loa is over 9 kilometers high, exceeding the height of Mount Everest above sea level. The volume of material composing Mauna Loa is roughly 200 times greater than that of the large composite cone Mount Rainier, located in Washington. A profile of Mauna Loa, Hawaii, the largest shield volcano in the Hawaiian chain. Note the size comparison with Mount Rainier, Washington, a large composite cone. B. Profile of Mount Rainier, Washington. Note how it dwarfs a typical cinder cone. C. Profile of Sunset Crater, Arizona, a typical steep-sided cinder cone. Smart Figure 5.13 Comparing scales of different volcanoes. Smart Figure 5.13 Full alternative text description. Like Hawaii's other shield volcanoes, Mauna Loa has flanks with gentle slopes of only a few degrees. This low angle is due to the very hot, fluid lava that traveled fast and far from the vent. In addition, most of the lava flowed through a well-developed system of lava tubes. Another feature common to active shield volcanoes is one or more large, steep-walled calderas that occupy the summit. Calderas on shield volcanoes usually form when the roof above the magma chamber collapses. This occurs after the magma reservoir empties, either following a large eruption or as magma migrates to the flank of a volcano to feed a fissure eruption. In their final stage of growth, shield volcanoes erupt more sporadically, and pyroclastic ejections are more common. The lava emitted later tends to be more viscous, resulting in thicker, shorter flows. These eruptions steepen the slope of the summit area, which often becomes capped with clusters of cinder cones. This explains why Mauna Kea, a more mature volcano that has not erupted in historic times, has a steeper summit than Mauna Loa, which erupted as recently as 1984. Astronomers are so certain that Mauna Kea is over the hill that they built an elaborate astronomical observatory on its summit to house some of the world's most advanced and expensive telescopes. Watch animation, volcano types. Kilauea, Hawaii's most active volcano. Volcanic activity on the Big Island of Hawaii began on what is now the northwestern flank of the island and has gradually migrated southeastward. It is currently centered on Kilauea Volcano, one of the most active and intensely studied shield volcanoes in the world. Kilauea, located in the shadow of Mauna Loa, has experienced more than 50 eruptions since record-keeping began in 1823. Did you know? According to legend, Pele, the Hawaiian goddess of volcanoes, makes her home at the summit of Kilauea volcano. Evidence for her existence is Pele's hair, thin, delicate strands of glass, which are soft and flexible and have a golden brown color. This thread-like volcanic glass forms when blobs of hot lava are spattered and shredded by escaping gases. Several months before each eruptive phase, Kilauea inflates as magma gradually migrates upward and accumulates in a central reservoir located a few kilometers below the summit. For up to 24 hours before an eruption, swarms of small earthquakes warn of the impending activity. Most of the recent activity on Kilauea has occurred along the flanks of the volcano, in a region called the East Rift Zone. The longest and largest rift eruption ever recorded on Kilauea began in 1983 and continues to this day, with no signs of abating. Smart Figure 5.14 Lava curtain extruded along the East Rift Zone, Kilauea, Hawaii. Concept checks 5.5. 1. Describe the composition and viscosity of the lava associated with shield volcanoes. 2. Are pyroclastic materials a significant component of shield volcanoes? 3. Where do most shield volcanoes form, on the ocean floor or on the continents? 4. Where are the best-known shield volcanoes in the United States? Name some examples in other parts of the world. Watch mobile field trip, Kilauea volcano. 5.6 Cinder cones. Describe the formation, size, and composition of cinder cones. As the name suggests, cinder cones are built from ejected lava fragments that begin to harden in flight to produce the vesicular rock scoria. These pyroclastic fragments range in size from fine ash to bombs that may exceed 1 meter in diameter. However, most of the volume of a cinder cone consists of pea to walnut-sized fragments that are markedly vesicular and have a black to reddish-brown color. In addition, this pyroclastic material tends to have basaltic composition. Cinder cones are built from ejected lava fragments and are relatively small, usually less than 300 meters in height. Smart Figure 5.15 Cinder cones. Smart Figure 5.15 Full alternative text description. Watch mobile field trip, SP crater. Although cinder cones are composed mostly of loose scoria fragments, some produce extensive lava fields. These lava flows generally form in the final stages of the volcano's lifespan, when the magma body has lost most of its gas content. Because cinder cones are composed of loose fragments rather than solid rock, the lava usually flows out from the unconsolidated base of the cone rather than from the crater. Cinder cones have very simple, distinct shapes. Because cinders have a high angle of repose, cinder cones are steep-sided, having slopes between 30 and 40 degrees. In addition, cinder cones have large, deep craters relative to the overall size of the structure. Although relatively symmetrical, some cinder cones are elongated and higher on the side that was downwind during the final eruptive phase. Most cinder cones are produced by a single, short-lived eruptive event. One study found that half of all cinder cones examined were constructed in less than 1 month, and 95% of them formed in less than 1 year. Once the event ceases, the magma in the plumbing connecting the vent to the magma source solidifies, and the volcano usually does not erupt again. As a result of this typically short lifespan, cinder cones are small, usually between 30 and 300 meters tall. A few rare examples exceed 700 meters in height. Cinder cones number in the thousands around the globe. Some occur in groups, such as the volcanic field near Flagstaff, Arizona, which consists of about 600 cones. Others are parasitic cones that are found on the flanks or within the calderas of larger volcanic structures. Paracutin, life of a garden variety cinder cone. One of the very few volcanoes studied by geologists from its very beginning is the cinder cone called Paracutin, located about 320 kilometers west of Mexico City. In 1943, its eruptive phase began in a cornfield owned by Dionisio Pulido, who witnessed the event. For 2 weeks prior to the first eruption, numerous tremors caused apprehension in the nearby village of Paracutin. Then, on February 20th, sulfurous gases began billowing from a small depression that had been in the cornfield for as long as local residents could remember. During the night, hot, glowing rock fragments were ejected from the vent, producing a spectacular fireworks display. Explosive discharges continued, throwing hot fragments and ash occasionally as high as 6,000 meters into the air. Larger fragments fell near the crater, some remaining incandescent as they rolled down the slope. These materials built an aesthetically pleasing cone, while finer ash fell over a much larger area, burning and eventually covering the village of Paracutin. In the first day, the cone grew to 40 meters, and by the fifth day it was more than 100 meters high. The first lava flow came from a fissure that opened just north of the cone, but after a few months flows began to emerge from the base of the cone. In June 1944, a clinkery AA flow 10 meters thick moved over much of the village of San Juan Parangaricutiro, leaving only remnants of the church exposed. After 9 years of intermittent pyroclastic explosions and nearly continuous discharge of lava from vents at its base, the activity ceased almost as quickly as it had begun. Today, Paracutin is just another one of the scores of cinder cones dotting the landscape in this region of Mexico. Like the others, it will not erupt again. The village of San Juan Parangaricutiro was engulfed by AA lava from Paracutin. Only portions of the church remain. Smart Figure 5.16 Paracutin, a well-known cinder cone. Concept checks 5.6. 1. Describe the composition of a cinder cone. 2. How do cinder cones compare in size and steepness of their flanks with shield volcanoes? 3. Over what time span does a typical cinder cone form? Watch Condor video, Cinder Cones and Basaltic Lava Flows. 5.7 Composite Volcanoes. List the characteristics of composite volcanoes and describe how they form. Earth's most picturesque yet potentially dangerous volcanoes are composite volcanoes, also known as stratovolcanoes. Most are located in a relatively narrow zone that rims the Pacific Ocean, appropriately called the Ring of Fire. This active zone includes a chain of continental volcanoes distributed along the west coast of the Americas, including the large cones of the Andes in South America and the Cascade Range of the western United States and Canada. Classic composite cones are large, nearly symmetrical structures consisting of alternating layers of explosively erupted cinders and ash interbedded with lava flows. A few composite cones, notably Italy's Etna and Stromboli, display very persistent eruption activity, and molten lava has been observed in their summit craters for decades. Stromboli is so well known for eruptions that eject incandescent blobs of lava that it has been called the lighthouse of the Mediterranean. Mount Etna has erupted, on average, once every 2 years since 1979. Just as shield volcanoes owe their shape to fluid basaltic lavas, composite cones reflect the viscous nature of the material from which they are made. In general, composite cones are the product of silica-rich magma having an andesitic composition. However, many composite cones also emit various amounts of fluid basaltic lava and, occasionally, pyroclastic material having a felsic composition. The silica-rich magmas typical of composite cones generate thick, viscous lavas that travel less than a few kilometers. Composite cones are also noted for generating explosive eruptions that eject huge quantities of pyroclastic material. A conical shape, with a steep summit area and gradually sloping flanks, is typical of most large composite cones. This classic profile, which adorns calendars and postcards, is partially a result of the way viscous lavas and pyroclastic ejected materials contribute to the cone's growth. Coarse fragments ejected from the summit crater tend to accumulate near their source and contribute to the steep slopes around the summit. Finer ejected materials, on the other hand, are deposited as a thin layer over a large area and hence tend to flatten the flank of the cone. In addition, during the early stages of growth, lavas tend to be more abundant and flow greater distances from the vent than they do later in the volcano's history, which contributes to the cone's broad base. As a composite volcano matures, the shorter flows that come from the central vent serve to armor and strengthen the summit area. Consequently, steep slopes exceeding 40 degrees are possible. Two of the most perfect cones, Mount Mayon in the Philippines and Fujiyama in Japan, exhibit the classic form we expect of composite cones, with steep summits and gently sloping flanks. Figure 5.17 Fujiyama, a classic composite volcano. Japan's Fujiyama exhibits the classic form of a composite cone, a steep summit and gently sloping flanks. Despite the symmetrical forms of many composite cones, most have complex histories. Many composite volcanoes have secondary vents on their flanks that have produced cinder cones or even much larger volcanic structures. Huge mounds of volcanic debris surrounding these structures provide evidence that large sections of these volcanoes slid downslope as massive landslides. Some develop amphitheater-shaped depressions at their summits as a result of explosive lateral eruptions, as occurred during the 1980 eruption of Mount St. Helens. Often, so much rebuilding has occurred since these eruptions that no trace of these amphitheater-shaped scars remain. Others, such as Crater Lake, have been truncated by the collapse of their summit. Concept checks 5.7. 1. What name is given to the region having the greatest concentration of composite volcanoes? 2. Describe the materials that compose composite volcanoes. 3. How does the composition and viscosity of lava flows differ between composite volcanoes and shield volcanoes? 5.8 Volcanic hazards. Describe the major geologic hazards associated with volcanoes. Roughly 1,500 of Earth's known volcanoes have erupted at least once, and some several times, in the past 10,000 years. Based on historical records and studies of active volcanoes, 70 volcanic eruptions can be expected each year. In addition, one large volume eruption can be expected every decade. These large eruptions account for the vast majority of volcano-related human fatalities. Today, an estimated 500 million people in places such as Japan, Indonesia, Italy, and Oregon live near active volcanoes. They face a number of volcanic hazards, such as destructive pyroclastic flows, molten lava flows, mud flows called lahars, and falling ash and volcanic bombs. Pyroclastic flow, a deadly force of nature. Some of the most destructive forces of nature are pyroclastic flows, which consist of hot gases infused with incandescent ash and larger lava fragments. Also referred to as nuées ardentes, these fiery flows can race down steep volcanic slopes at speeds exceeding 100 km per hour. Pyroclastic flows have two components, a low-density cloud of hot expanding gases containing fine ash particles and a ground-hugging portion composed of pumice and other vesicular pyroclastic material. These pyroclastic flows occurred on Mount Mayon, Philippines, during the 1984 eruption. Pyroclastic flows are composed of hot ash and pumice and are blocky lava fragments that race down the slope of volcanoes. Residents running away from a pyroclastic flow that reached the base of Mount Sinabung, Indonesia, 2014. Figure 5.18 Pyroclastic flows, one of the most destructive volcanic forces. Driven by gravity. Pyroclastic flows are propelled by the force of gravity and tend to move in a manner similar to snow avalanches. They are mobilized by expanding volcanic gases released from the lava fragments and by the expansion of heated air that is overtaken and trapped in the moving front. These gases reduce friction between ash and pumice fragments, which gravity propels downslope in a nearly frictionless environment. This is why some pyroclastic flow deposits are found many miles from their source. Occasionally, powerful hot blasts that carry small amounts of ash separate from the main body of a pyroclastic flow. These low-density clouds, called surges, can be deadly but seldom have sufficient force to destroy buildings in their paths. Nevertheless, in 2014, a hot ash cloud from Japan's Mount Ontake killed 47 hikers and injured 69 more. Pyroclastic flows may originate in a variety of volcanic settings. Some occur when a powerful eruption blasts pyroclastic material out of the side of a volcano.